What's up, bitches? In this video, I'm going to teach you guys about transform solutions for first order linear models, okay? So, all you want to know for this chapter is one equation, okay? Well, basically one equation, which is this. Y dot equals 1 over tau y equals f of t, okay? F of t, this is your input function, whatever. And y is your system's response. Okay? So anything that's first order, you're going to follow this equation, and the answer is going to be this. Your system's response is going to be this. The steady state response plus initial value negative the steady state response times e to the power of negative t divided by the time constant, which is tau, okay? You have to know these usually they should be in your crib sheet or your formula sheet, but if they're not, you really have to know them by heart. And that's it. It's really not rocket science. But you have to understand that, hold on, let me explain. YSS, steady state, is basically the system's response when, like, at infinite time, okay? So usually when you try to find YSS, you just have to set y equals 0 and solve this f of t, okay? And yeah, that's it. This would be YSS. And that's pretty much how you find YSS. The initial response, usually when you answer, like when you're doing your questions or your exam, this should be given, but it's just the initial thing. And that's it. That's all you have to know. For this chapter, you might also want to use Laplace transforms, okay? So let's do an example just to practice. So this question, it's asking, well, it's giving us a system over here, this mechanical system, so it's pretty easy. And it's just asking you to sketch the response, like y of t, when the input VA is 0 and the initial velocity is 10, okay? So just like every mechanical system, we start with the free body diagram, M. And there's also point A. Okay. So when you're solving a mechanical system, you always want to begin with the body that has the input, which in this case it's A. It's VA. This is our input. And since there's no mass, there's no inertia, but we do have a damper behaving this way. B3. Now, normally, wait, let me change colors. Okay, there you go. So usually, the way you do this when the damper or a spring gets connected to another body, you just pretend that this is a wall over here. If that was the case, it would have just been VA. But since this massive block is also moving that way, it's gonna undo some of the velocity, okay? Hold on, let me make some room. Damn. Fuck. Oh my god, bro. My bad, guys. There you go. Okay. V3, VA negative. We're gonna call it velocity 1. Okay? That's it. Let me make some room. Whoops. Let me make some room. Shit works. Now, let's go on to this block thing. Holy shit, what a piece of shit app. My bad, guys. Alright. This. Following Newton's law, basically, the body, this block, it's going to be the same force from the damper, just the opposite direction because it's a different object, right? It's the same thing as if you're like pushing onto a box. And if you're pushing it that way, the box is going to push it the opposite way. It's the same principle here. So that way it's going to be V3, VA negative V. It's moving this way, so its inertia is going to push the opposite way, m times its acceleration. And then there's basically two dampers, B1V and B2V. Since one of them is on the ground and the other one connected to a wall, you don't need to subtract anything, okay? And then you just write the formula, okay? We just want to study. We just need this one over here because V of A is already considered in this free body diagram. So whatever's on this side is equal to whatever is on that side. That's all you need to do. Oops. MV dot plus, I'm just going to factorize the V. B1 plus B2 equals B3 VA negative V. I'm going to distribute B3 and I'm going to send this V to the other side. So we would get this. And I'm also going to factorize it. B1 plus B2 plus B3 equals B3 VA. Now, remember that we have to follow this formula. Equals F of t, which is the input, but in this case it's A of t, whatever. Okay? There has to be no scalars or any constants in front of our what do you call it? System's response, the derivative of our system's response. We're not supposed to have this m. So we're just going to divide everything by m. So we would get this plus b1 plus b2 plus b3 divided by m v equals b3 over m and our input, and that's it. So we basically have our time constant over here. It's just going to be the inverse of that. Equals m divided by b1 plus b2 plus b3. All right. Next. Now we could move on to whatever is asking over here. Okay? I'm just going to move down a little bit. So it said that the input is 0 and fuck, how do you do an ampersand? Whatever. And the initial velocity is 10, right? That's what it's saying. Yeah, there you go. All right. So remember that the answer for this equation is this. T equals VSS, as I explained earlier, plus, again, sorry, V of 0, negative VSS E negative T over tau. Okay? So VSS is basically the step response at t equals infinity. It's like the steady state. That's what it's called. Okay? And you find it by setting v dot equals 0. So then we would get 0 plus b1 plus b2 plus b3 over m v equals b3 m v a. However, the problem states that VA, the input, is equal to 0. So this VSS that we're trying to solve is just going to be equal to 0, okay? You kind of don't need to know this. If the input is 0, then at infinite times, nothing's going to move, right? Because you're not applying any force, okay? So VSS is 0. You could just forget this shit. And next we have V of 0, so we're ready to solve. V of t equals 10 times e to the power of t. And, oh, this is going to be huge. Times m divided by b1 plus b2 plus b3. That's the answer. There you go. Now, to sketch it, you kind of have to understand what these numbers mean, okay? Okay, here, this is how I'll explain it, okay? When you have a step response equals whatever. Wait, actually, let me write it, just so it's easier for you guys to understand. YSS plus Y0 negative YSS E negative tau. Okay, so if tau, your time constant, is more than 0, then you're going to have a steady response, okay? This is your... What the fuck just happened? This is your initial condition. it's going to be steady like this. It's going to go down. Okay. But if your time constant is more than 0, then it's going to be unstable. It's going to go up to infinity, and it's going to be like, well, it's not going to be hard to simulate it, but that's how it's going to behave. If your time constant is infinite, then it's going to move constantly. Okay. By the way, these graphs, it assumes 0 response that I'm drawing right now. Okay. So then our answer would just be this one, because tau is going to be more than 0, right? The mass is larger than the all the mass damper constants. So our final answer would be this: y t 10. What's the initial condition? It's going to go down like this. The time constant, basically, actually, let me draw it larger. There you go. 10 goes down like this. Basically, this part over here, this line, is going to be the slope, and over here is your time constant. That's how the linear models are, well, that's how they're modeled, okay? Now, in another case, let's pretend we do have an input, okay? There's 3 scenarios. One, something's going to look like this. This is when your steady state response is not equal to 0. And over here is when your you have an initial condition. If your initial condition is equal to 0, then it would just be this. It would just be the same thing, just down to 0. Now, if your steady state response is equal to 0, then it would be going down like this. And that's it. That's how you solve your first order linear transient transform models. Thank you for watching.